In a universe teeming with celestial wonders and cosmic enigmas, a dire warning echoes through space's interstellar expanse, reaching Earth. A gargantuan celestial body has begun sending radio messages towards our planet. What could be the source of these perplexing signals? The answer lies in the heart of the cosmos, billions of light-years away. This intriguing space saga calls upon us to traverse vast cosmic distances, to listen intently to the cryptic whispers of the cosmos and probe one of the universe's most enigmatic phenomena, the enigma of fast radio bursts, FRBs. Fast radio bursts, FRBs, are enigmatic flashes of light that momentarily grace our cosmos with their fleeting presence. Lasting a few milliseconds, these intense flares of radio waves permeate space with an energy equating to what our sun produces in an entire year. Despite their ephemeral existence, these cosmic phenomena carry a profound mystery that has enthralled the scientific community and sent ripples of intrigue through the world of astrophysics. Since their first detection in 2001, over 1,000 FRBs have been observed, albeit not without challenges. These fast and furious bursts emerge without warning. Their unpredictable nature makes them a spectral figure in the cosmic landscape. Like flashes of a cosmic lighthouse lost in the depths of the universe, FRBs are transient, mysterious, and pose many questions to curious earthbound observers. One of the primary conundrums associated with FRBs is their origin. How can such powerful bursts of energy be created in mere milliseconds, and where in the vast cosmic landscape do they originate? This quandary has led scientists to contemplate various scenarios from colliding neutron stars to flaring magnetars and even the speculative whisper of extraterrestrial civilizations. Yet, despite these compelling hypotheses, the exact nature of these bursts remains elusive. What is known, however, is that these signals travel unimaginable distances, journeying from galaxies billions of light-years away to reach our radio telescopes. Their journey through the cosmos is marked by trials and tribulations, distorted by interstellar medium and cosmological factors. Among the captivating features of FRBs is their surprising diversity. No two bursts are the same. They vary in intensity, wavelength, polarization, and dispersion. It's this variability that adds another layer of intrigue to the enigma of FRBs. These cosmic flashes of light are like cosmic messengers, each carrying a unique tale of its birth, its voyage through the cosmos, and its final arrival at our terrestrial doorstep. In the constellation of cosmic phenomena, fast radio bursts stand as one of the most captivating mysteries. Their elusive nature and energetic prowess have turned them into subjects of intense scrutiny and speculation. As scientists delve deeper into their nature and origins, these signals from the far reaches of the universe continue to baffle and fascinate. Teasing us with glimpses of a universe far beyond our immediate perception, they urge us to probe further, listen more intently, and seek to decipher the cryptic messages embedded in their fast and furious flashes. The study of FRBs is not just an astrophysical endeavor. It is a quest to understand the universe's broader narrative. By studying these enigmatic signals, we tap into an intergalactic discourse, attempting to decode the cosmic language, seeking answers that may help illuminate our place in the grand cosmic orchestra. As we stand on the precipice of these great cosmic mysteries, the enigma of fast radio bursts compels us to gaze up, listen, and wonder. The history and discovery of FRBs. The fascinating tale of the discovery of fast radio bursts, FRBs, began with an archival deep dive in the early years of the 21st century. The astronomical community was first introduced to this novel cosmic phenomenon through an article published in 2007, but the saga had started much earlier. The story of FRBs began in 2001 with the Lorimer burst, the first recorded instance of such a burst. Dr. Duncan Lorimer, an astrophysicist, and his student, David Narkovich, while investigating archived data from the Parkes Observatory in Australia, stumbled upon an unexpected anomaly. The data, captured in 2001, showed a sudden, intense spike of radio waves that lasted a mere 5 milliseconds. The burst, originating from a region outside our galaxy, was unlike anything astronomers had seen before. Initially met with skepticism, the Lorimer burst set the stage for a new chapter in radio astronomy. In the years following the Lorimer burst, the global scientific community was abuzz with conjecture and speculation. The discovery of such high-energy, short-lived bursts, distinct from the slow and regular pulses of known pulsars, was indeed perplexing. They were so odd and unexpected that some speculated they could even be a product of human-made interference or observational artifacts. The initial skepticism and the esoteric nature of FRBs meant that progress in understanding these mysterious signals was slow. The second fast radio burst wasn't detected until 2012, once again at the Parkes Observatory. This second event, FRB 010724, rekindled interest in the phenomena, affirming that the Lorimer burst was not an isolated event or a fluke, but indicative of a novel and perplexing cosmic phenomenon. By 2013, the astrophysical community had started to accept the reality of FRBs, though their origin and nature remained shrouded in mystery. The detection of 4 more bursts by Parkes, presented at the meeting of the American Astronomical Society, sparked a wave of renewed interest. These detections provided substantial evidence that FRBs were real and not merely observational artifacts or terrestrial interference. In the following years, other observatories worldwide joined the hunt for these cosmic flashes. Radio telescopes such as the Green Bank Telescope in West Virginia and the Arecibo Observatory in Puerto Rico began to detect and catalog FRBs, adding to the global dataset. However, the real breakthrough came in 2015 with the detection of FRB 121102. Unlike its predecessors, this FRB was not a solitary event. Instead, it repeated, sending multiple bursts of radio waves, giving scientists a second, third, and more chances to observe and study its properties. FRB 121102, the first known repeating fast radio burst, became a vital key to understanding these cosmic conundrums. Since the detection of FRB 121102, our understanding of these mystifying bursts has continued to grow, though they remain largely mysterious. New instruments, like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, have further revolutionized the search for these bursts. CHIME's wide field of view and digital capabilities have increased the rate of FRB detection, shedding more light on their distribution and diversity. As we continue on this cosmic journey, the history of FRBs unfolds like a captivating interstellar detective story. From the initial surprise of the lore, the nature and characteristics of FRBs. Fast radio bursts, FRBs, are one of the most intriguing puzzles of modern astrophysics, and their elusive and ephemeral nature contributes greatly to their intrigue. These extragalactic radio wave bursts manifest as brief, intense flashes that last just a few milliseconds. Despite their brevity, FRBs are remarkably luminous, releasing more energy in a fraction of a second than the sun does in days, weeks, or even months. One of the defining characteristics of FRBs is their dispersion measure. The dispersion measure is a property of radio signals traveling through space, particularly through the ionized interstellar and intergalactic medium. As these radio waves traverse the cosmos, they interact with the electrons in the interstellar medium, causing the waves of lower frequency to slow down more than those of higher frequency. This results in a dispersion or smearing of the signal over time. The greater the dispersion measure, the farther the signal has traveled. Remarkably, the dispersion measures of FRBs are so high that they are believed to originate from vast cosmological distances. Another intriguing aspect of FRBs is their irregular occurrence. While most FRBs have been observed as one-off events, a subset known as repeating FRBs sends multiple bursts over time. The first of these repeating FRBs, FRB 121102, was discovered in 2015 and is still active, regularly sending bursts of radio waves that scientists continue to monitor and study. The existence of both single and repeating FRBs suggests a range of astrophysical mechanisms behind these fascinating events. The spectra of FRBs also provide invaluable clues to their nature. The broadband nature of these bursts, spanning frequencies from hundreds of megahertz to several gigahertz, is consistent with a cosmic origin. Additionally, some FRBs show frequency-dependent structure, including downward drifting subbursts or band-limited structures, hinting at complex emission processes. Despite the numerous detections and extensive studies, the precise location of most FRBs remains elusive. For a few repeating FRBs, however, researchers have managed to localize their origins to specific galaxies. For example, FRB 121102 was traced back to a dwarf galaxy located roughly 3 billion light-years away. This breakthrough provided the first solid evidence that FRBs originate outside the Milky Way. The rapid timescales of FRBs indicate that the sources of these bursts are likely to be compact, no larger than a few hundred kilometers across. This is similar in size to neutron stars, which are dense remnants of supernova explosions, leading many to propose that these exotic objects could be responsible for some FRBs. The transient nature of FRBs, combined with their vast distances, makes their study particularly challenging. These intriguing bursts appear and disappear in the blink of an eye, leaving only their faint echoes in our radio telescopes. Yet, these fleeting whispers from distant corners of the universe hold the potential to unlock new understanding of the cosmos. Each observed characteristic, from their dispersion measures and spectral properties to their spatial distributions and repetition behavior, is a piece of the enigma that is FRBs. Their nature and characteristics encapsulate the boundless wonders of our universe and our ceaseless pursuit to decipher them. The unusual FRB patterns and neutron stars. The discovery of FRBs opened a new window into the high-energy universe, with their unique characteristics challenging our understanding of astrophysical phenomena. One of the many enigmas associated with FRBs is their unpredictable and somewhat unusual patterns. This, in combination with other properties of FRBs, has led scientists to investigate the potential role of neutron stars, the incredibly dense remnants of massive stars, as a source of these phenomena. Neutron stars, despite their small size, typically around 20 kilometers in diameter, pack a mass greater than that of our Sun. They are known for their strong gravitational and magnetic fields, often leading to extreme environments that are thought to be conducive to the creation of FRBs. Observations of FRBs have revealed a striking variety in their patterns. While many FRBs appear to be solitary events, some exhibit repeating patterns. This includes FRB 121102, which not only repeats but does so in a non-periodic fashion, challenging our understanding of these enigmatic events. Another intriguing FRB, designated as FRB 180916, J0158 plus 65, was found to follow a 16-day repeating cycle, with bursts occurring for a few days before a period of silence, adding another layer to the mystery. In the magnetar model, the intense magnetic field of the neutron star, billions of times stronger than any man-made magnet, is thought to play a crucial role. The stress induced by the magnetic field can cause the star's crust to crack, releasing a burst of magnetic energy that can give rise to an FRB. For repeating FRBs, one hypothesis is that a rotating magnetar could release bursts each time a hotspot on its surface comes into our line of sight. The unusual patterns of FRBs could also be explained by the interaction of a neutron star with its environment. For example, if a neutron star were part of a binary system or was surrounded by an accretion disk, the interaction of the star with the matter around it could create the conditions necessary for an FRB to occur. The observed patterns would then be influenced by the orbital dynamics of the system or the star's interaction with the disk. These models, while promising, are yet to fully account for the diverse properties of FRBs, and many questions remain. For example, why do some neutron stars emit FRBs while others do not? And why do we see such a wide range in the timing patterns of repeating FRBs? The connection between FRBs and neutron stars remains speculative, and further observations are crucial to testing these models. With each new discovery, however, we get a step closer to understanding these enigmatic phenomena. As we continue to observe and catalog FRBs, the unusual patterns they exhibit will undoubtedly continue to inform and refine our theories, offering new insights into the extreme physics of neutron stars and the vast, complex universe beyond our galaxy. The radio universe and its sounds. The universe, when perceived through the lens of a radio telescope, presents us with an intriguing symphony of sounds. Much like a vast ocean brimming with life, the radio universe is awash with signals. From the pulsating rhythms of pulsars to the abrupt bursts of FRBs, each bearing a unique signature, revealing secrets of cosmic phenomena. Radio waves from space are not sound waves, but are a form of electromagnetic radiation similar to visible light, but with longer wavelengths. While we cannot hear these radio waves directly, they can be converted into sound waves, transforming the silent universe into a celestial concert. Pulsars, a type of neutron star, are well-known composers in the radio universe. These spinning stars emit beams of radio waves from their magnetic poles. When a beam sweeps past Earth, it creates a pulse of radio waves, akin to the lighthouse effect. As pulsars spin with extreme consistency, the resulting pulses provide a steady rhythm, a cosmic metronome ticking away in the radio universe. Adding to this cosmic orchestra are FRBs, the focus of this book. Unlike the regular rhythm of pulsars, FRBs are akin to sudden crescendos, brief, bright, and utterly unpredictable. Their origin remains elusive, but their influence is unmistakable. Each burst, lasting just a few milliseconds, carries with it invaluable information about the universe's most enigmatic corners. Lastly, our own galaxy, the Milky Way, adds its verse to the radio symphony. Our home galaxy is a cacophony of radio noise, with the galactic center buzzing with activity from supernova remnants, pulsars, and other high-energy phenomena. All these signals blend together to form the persistent hum of our galaxy in the radio universe. In this radio universe, every celestial body and event that emits radio waves adds a note, a rhythm, or a melody to the symphony. By listening to these sounds, astronomers can probe the universe's depths, uncovering secrets hidden from our eyes. In this pursuit, radio telescopes serve as our cosmic ears, capturing the universe's sounds across vast distances and timescales. FRBs, with their unexpected bursts, have added a new level of excitement to this ongoing cosmic concert. Their elusive nature has sparked a sense of mystery and curiosity, prompting scientists worldwide to tune in to their signals. As we continue to decipher these cosmic signals, we edge closer to understanding the universe's profound depths, and perhaps even our place within it. For now, the radio universe continues to sing its celestial symphony, an ever-evolving melody awaiting our interpretation. Theories and speculations on FRBs and extraterrestrial life. The world of astrophysics is one where the line between scientific hypotheses and wild speculation often blurs, and this is particularly true when it comes to FRBs. The enigmatic nature of FRBs has led to a plethora of theories regarding their origins, and among the most tantalizing is the possibility of an extraterrestrial civilization. While many scientists approach the alien hypothesis with understandable skepticism, it's an idea that has nonetheless captured the public imagination. Could these mysterious, ultra-powerful signals be the work of an advanced civilization attempting to communicate or power interstellar spacecraft? Let's explore some of these theories and their plausibility. The first and most popular hypothesis involves FRBs as a means of interstellar communication. If this were the case, FRBs could represent an advanced form of information transmission, akin to our own radio broadcasts, but on an immensely greater scale. Given the energy involved, any civilization capable of creating such signals would likely be a Type 2 or Type 3 civilization on the Kardashev scale, having harnessed the power of an entire star or galaxy. While this idea is fascinating, the brief and non-repetitive nature of most FRBs makes decoding any potential message highly challenging. A second theory suggests that FRBs might be the byproduct of advanced propulsion systems. Harvard astrophysicists Avi Loeb and Manasvi Lingam proposed the idea that FRBs could be evidence of extraterrestrial technology. In their 2017 paper, they argued that these radio bursts could be leakage from powerful beam-powered propulsion systems used by advanced spacecraft. They theorized that an alien civilization might be using a planet-sized transmitter to propel enormous spacecraft, and the sweeping beams from this transmitter might be the FRBs we detect. However, the massive energy requirements and the technical challenges of building such a transmitter make this hypothesis highly speculative. A third, and perhaps most far-fetched theory posits that FRBs could be cosmic SOS signals. Some have speculated that these radio bursts could be distress signals or warning beacons from civilizations facing cataclysmic events, such as the explosion of a star or a collision with another celestial body. However, as with the other hypotheses, the lack of a pattern or discernible message in FRBs makes it difficult to substantiate such a claim. However, the field of SETI, search for extraterrestrial intelligence, is in itself a testament to our willingness to consider and explore the idea of intelligent life beyond Earth. While our understanding of FRBs remains in its infancy, the mere possibility of a link to extraterrestrial civilizations keeps our curiosity piqued and pushes us to dig deeper into these cosmic enigmas. In the grand scheme of things, the speculation surrounding FRBs and extraterrestrial life serves as a reminder of our place in the cosmos. As we ponder on the nature of these intense radio bursts, we are ultimately exploring our understanding of the universe and our potential place within it. Whether or not FRBs are the work of distant civilizations, their study continues to broaden our knowledge of the cosmos and the myriad mysteries it holds. The search for extraterrestrial intelligence and theories of communication. The search for extraterrestrial intelligence, also known as SETI, has been a vibrant field of research for several decades. It's based on the idea that if there are civilizations beyond Earth, they may be trying to communicate, just as we have sent out our own messages into space. This chapter delves into the various theories and methods employed by SETI in the hopes of uncovering intelligent life in the cosmos. SETI's methods are grounded in the assumption that an advanced civilization might use methods of communication similar to those we've developed on Earth. This premise has led to a focus on the electromagnetic spectrum, with specific attention paid to radio and optical signals. These signals can traverse vast distances in space without significant interference, making them ideal for long-distance communication. One significant project in SETI's history was the launch of the Arecibo message in 1974. A simple depiction of our solar system, human DNA, and other fundamental aspects of life and culture on Earth, the message was sent via modulated radio waves towards a cluster of stars some 25,000 light-years away. It was humanity's first intentional message to the stars, an attempt to reach out and say, "We are here." Yet as we contemplate the possibility of receiving a message, the question arises, what form might such a message take? This is where the theories of communication come into play. The Drake equation, formulated by Frank Drake in 1961, is often used to estimate the number of civilizations with which we could potentially communicate. It takes into account factors like the rate of star formation, the fraction of stars with planetary systems, the number of planets that could potentially support life, and the lifespan of technologically advanced civilizations. Even as we contemplate these questions, we must also grapple with the challenges of our own limitations. The Fermi paradox, named after physicist Enrico Fermi, posits a contradiction between the high probability of extraterrestrial life and the lack of contact or evidence for such civilizations. Are we looking in the wrong way or at the wrong time? Or is it possible that advanced civilizations self-destruct or retreat into a post-biological existence before they can make significant contact with others? In the quest for extraterrestrial communication, the mystery of FRBs has added another layer to the conversation. Are they naturally occurring phenomena or signals sent by an advanced civilization, as we've speculated in previous chapters? The search for extraterrestrial intelligence is not just a search for life beyond Earth. It is also a search for a deeper understanding of ourselves and our place in the universe. It forces us to question our assumptions, broaden our understanding, and continually push the boundaries of our knowledge. It is a testament to the spirit of human curiosity and our unending quest to reach beyond our own existence and into the heart of the cosmos. Technology's role in decoding cosmic signals. Technological innovation has always been at the heart of astronomy, enabling scientists to see farther and more clearly into the cosmic expanse. As we strive to decode the enigma of fast radio bursts, FRBs, the role of technology becomes even more crucial. The story of technology's role begins with the creation of the first radio telescopes, but merely receiving these radio signals is just the beginning. The complexity and vast amounts of data involved require significant computing power to analyze and interpret. This is where technologies like machine learning and data science become incredibly valuable. They help sift through the torrents of data, identifying patterns and signals that may be indicative of novel astronomical phenomena or even potentially extraterrestrial communications. A recent example is the application of machine learning algorithms to the analysis of FRB data. By feeding these algorithms large amounts of FRB data, scientists have trained them to recognize and classify different types of FRBs, aiding in the discovery of new repeating FRB sources. This would have been nearly impossible without the scalability and pattern recognition capabilities offered by these technologies. The Square Kilometre Array, SKA, an international effort to build the world's largest radio telescope, is a vivid example of technology's immense role. Upon completion, it will possess a total collecting area of approximately 1 square kilometer. By scanning the skies more rapidly and with greater sensitivity than any previous telescope, it will help usher in a new era of discovery in radio astronomy, potentially revolutionizing our understanding of FRBs. Technological advancement, however, is not solely about building bigger and better equipment. It also involves refining and optimizing existing tools. Techniques like fast-folding algorithm, FFA, for pulsar detection, for instance, have been optimized to find FRBs, lending to a more effective way to decode these enigmatic signals. The enigma of fast radio bursts continues to be one of the most intriguing puzzles in radio astronomy. As we delve deeper, each discovery unveils new questions and deeper mysteries, reminding us of our place in the vast cosmic theater. With the ever-advancing technologies and novel approaches in the field, our understanding of the radio universe is bound to expand. The future of radio astronomy, we anticipate, will carry a symphony of cosmic sounds, some familiar, some exotic, and perhaps some that whisper tales of other worlds and civilizations, pushing the boundaries of human understanding into the uncharted realms of the cosmos.